Today's video will demonstrate how to compute algorithmic efficiency through instrumentation. Hello, I'm James Helfrich. The main way we determine algorithmic efficiency is by inspecting the code. However, sometimes we're just not sure we got the right answer. Another method is called instrumentation, and here we put counters in the code, display the output of how many times a given line of code was executed, and plot it. And through the shape of the curve, we can determine the algorithmic efficiency. This video will demonstrate this process. Instrumentation is the process of adding counters to an existing algorithm which does not change the functionality of the task being measured. Instead, instrumentation measures how the task was performed. There's 3 steps to the process. Number 1 is add code. You want to add code specifically to counting the number of times a key part of the algorithm is executed. The goal is we don't actually want to impact the code, we just want to add a counter. Number 2, generate a report. Have the code create a table where each row corresponds to a single run and the columns track the input size versus execution time. And number 3 is interpret the results. Based on the generated report, characterize the various levels of algorithm performance. So let's take a look at an example here. This happens to be C++. We want to add counters to tabulate the number of times a given part of the code was executed. And we care about is the code inside the inner for loop. So step number 1, I'm going to add a counter. So citer is count for iterations. I'm going to initialize it to 0. Then I'm going to add that count iter inside the for loop. So every time that line gets executed, my count iter is going to increase by 1. And then at the end, I'm going to output the results. And this will tell me what for the given value of n, the passed parameter, and how many times count iter was called. Whenever adding instrumentation code or any other debug code designed to gain insight into how algorithm works, an important goal is to avoid impacting the outcome of the program. In other words, the instrumentation code should only count how often a given line of code is executed. It should not change anything else. All right, the next step is to generate the report. Here I'm going to run it with 4 test cases, 8, 16, 32, and 64. Now I chose those very specifically because they double each time. And an important indicator of algorithmic efficiency is what happens when the number of elements is doubled. By instrumenting our code, we can obtain a measure of how many times a given statement is executed. One measurement, however, is not sufficient to determine the algorithmic efficiency. Though we can often validate our big O calculations with just 1 or 2 measurements, it is often better to have several rows of data in our table. Each level of algorithmic efficiency is characterized by what happens when input size is doubled. Now, with O sub 1, doubling doesn't change a thing. O sub log n, doubling the size of the input slows execution by 1 time unit. O sub n, double the size of the input, doubles the execution time. N log n will double execution time plus 1. N squared will quadruple execution time. And 2 to the n, increasing the size of the input by 1, will actually double the execution time. Now, the shape of the curve, if we graph it, will also describe the efficiency. O sub 1 is a flat horizontal line. O sub log n curves to a nearly horizontal line. O sub n is a straight diagonal line. N log n curves up and then becomes nearly straight and diagonal. N squared looks just like a parabola. And 2 to the n looks like an extremely steep parabola. So let's take a look at our data here. Let's see here. How's that going to be? And here's my graph. So it's not O sub 1 because it's not flat and the count is not constant. It's not log n because it's definitely increasing the slope as we go. It's not n because it's not a straight diagonal line. So it could be n log n or n squared. For both of these, the shape of the curve is nearly the same. However, looking at the output, we can see that we are basically quadrupling the cost, the C column, for every doubling of n. So that sounds like n squared. You can learn more about instrumentation in the instrumentation section of the efficiency chapter of the software design textbook.